Assalamualaikum warahmatullahi wabarakatuh. So guys, welcome back to my video, and we will continue with chapter number 4 on the topic of three-phase power calculation. And alright, so this is some of the learning outcomes. Where number 1, so you must be able to calculate complex power. So in terms of apparent power, active and reactive power. Right, so this is basically the S. Right, so this is a P, and reactive power, so the symbol is Q. And also the power factor in balanced and unbalanced three-phase circuits. Right, so some of the review of complex power calculations. So the first one is a power observed by a pure resistor. So just consider a pure and linear resistor. So as shown in this figure, right, so this is the linear resistor. So where we assume that the resistor is excited by a sinusoidal input voltage. So this is the signal of the input of the sinusoidal input, Vt equal to Vm cos omega t, and the terminal current has reached its steady state value where It equal to Im cos omega t. So this is the value for I, and this is the input value for V. Okay, so of course this is in a time domain, right? So since this is in sinusoidal waveform, so the input current and input voltage in phasor form are, first, this is I equal to Im over square root 2. So this is one you convert to phasor form. So you will get the IRMS value, the root mean square value of I with 0 angle. Okay. So this is for the maximum or the peak value. So divided by square root 2. So you will get the IRMS. Okay. So the one in this blue color. And then what happened to the voltage? So V equal to Vm over square root 2, 0 angle. And then this will give us the V RMS, okay, which is plotted here in red. So to say that they are in the same phase or in the same direction. Okay. So this is basically for a resistor. Okay, there's a complex power. So delivered to the resistor is defined to be S equal to V times I conjugate. So what's the meaning of I conjugate? So it's the complex conjugate of the current I, therefore, so S equal to VI conjugate equal to VRMS 0 degree multiplied by IRMS 0 degree. So this gives us VRMS IRMS 0 degree. So just in case you have a certain value or certain what do you call it, this negative or positive signage, so the value of conjugate will opposite. Okay, so we will see later in the capacitive and also in the inductive. Okay, capacitor or inductor. So in a rectangular form, S equal to VRMS IRMS cos theta, cos 0 plus VRMS IRMS sine 0. Okay, since we have 0 angle over here, since these two are 0. So once we convert into a rectangular form, so we will get the real value with cos theta, and this is the imaginary value with sine theta. So just substitute the value of 0 and 0. So this can be written as S equal P plus JQ. So where the real value of P is called the average real or active power and has the units of the watts. Okay. And then what happened to Q? Q is actually imaginary value of S. Okay. The complex power. So it's called the reactive power and has the units of VAR, VAR. So that's for resistor. So the real value of S, which is P, equal to VRMS, IRMS cos theta. So this is equal to VRMS, IRMS because cos theta equal to 1. Okay. So we got the value of the equation of P, which is equal to VRMS, IRMS, and this is the unit of P, which is watts, and Q, all right, the reactive power is actually the imaginary, again, is actually the imaginary value of S, and after you substitute the value of 0 angle, so this will give us value of 0. So 0 multiplied by I and V, so you will get 0, 0 var. Okay. So note some additional notes. This last result tells us that a pure resistor does not consume reactive power. So it doesn't consume reactive power because Q is 0. So reactive power because Q is 0. Okay. And then the power triangle for pure resistor is shown below. Right, since we don't have any imaginary value, okay, which is equal to Q, so we can clearly see that there is no any value, negative value, even negative value for Q or positive value for Q at the imaginary axis, y-axis. So figure power triangle for resistor. So we can conclude that S is actually equal to P and Q is somehow 0. Okay, so this is the phasor where S equal to P. Okay. So note the complex power S contains all the information pertaining to the power absorbed by a given load, because we know that complex power S, or this is equal to P plus JQ. All right, so all the information pertaining according to the power in terms of Q and P is actually shown in S. So the real power P represents the only useful power derived to the load. This is how we can understand or can define the the meaning of real power. Okay, and then the reactive power Q. So what does it mean? So it represents the energy exchange between the source and reactive part of the load. So it is being transferred back and forth between the load and the sources. Okay, this is the description of Q. What can you actually understand? The definition or how it works. Okay, so the modulus of S. So the modulus of S is called apparent power. Okay, it's called apparent power. So inductor. So now we come to the second part, which is complex power absorbed by a pure inductor. So we just assume a pure and linear inductor. So we have a pure and linear conductor over here. So let us again a sinusoidal current IT. So we do have the sinusoidal waveform IT, for example, in the time domain, of course, of amplitude Im, and the frequency omega to 2 pi f be fed into the inductor where IT equal to Im sine omega t. So this is actually equal to Im cos omega t minus 90. Okay, so this is how you can actually exchange the value or from sine omega t. Okay. So the voltage drop across the inductor is related to the current IT via the relation Vt equal to L di over dt. So this is the voltage drop, okay, over here, okay, in between the linear inductor. All right, so which is related to the current over here. So just substitute this value IT into this equation IT. Okay, so you may get d Im sine omega t over d dt. So derive or differentiate this equation will give us omega L Im cos omega t. Okay, so where we can actually represent WL I over here, all these parameter into V into Vm. Okay, so where Vm equal to omega Lim is the amplitude of the voltage drop across the inductor. Sorry. Okay, so again, so we can say that the Vm is actually the voltage drop across the or between the inductor linear or linear inductor. Okay, so we have done with the analysis of the voltage drop, and now we jump to the phasor form. So we have the I again. So this is the RMS value. So this is the RMS value over here. So we have the magnitude current or peak current over square root 2. So with angle of minus 90 degree. All right. So we have over here again. This is taken from this relationship. Okay. So we have minus 90 degree over here. Okay. So we put it here. Okay, for the I, and solve the equation, we get the I RMS with angle of minus 90 degree. Okay, so again, the blue color over here is representing I RMS. Okay, so with angle of 90 degree. Okay, and then what about the V? So V equal to Vm again over square root 2, and we obtain the value of the RMS with zero angle. All right, so this is the VRMS. We plot at the x-axis with zero angle, of course. So complex power S consumed by inductor. So we have this equation where S equal to VI conjugate. So remember, this star symbol is complex conjugate of the current I. Okay. So VRMS, so substitute into this S equal to VI. So we have VRMS 0 degree multiplied by IRMS 90 degree. So now we can see the function of conjugate. So here we have negative sign, but once you conjugate, all right, so this is the symbol of star. So we have now IRMS with 90 or positive 90 degree ampere. Okay, so this is how you do with the conjugate operation. Okay, instead of negative, now you have positive. Same goes over here. So you have now positive 90. So solving S equal to VRMS IRMS 90 degree. And now you try to expand this equation. So we have both the real plus the imaginary value. So where the real represented by cos 90 degree and imaginary represented by sine 90 degree. So cos 90 degree equal to 0. That's why, so multiply by VRMS, RMS, IMS, so will give us absolutely 0 value. Okay, but somehow sine 90 equal to 1 multiplied by VRMS, IMS, so you will still get the VRI RMS value at the imaginary part. Okay, J. So thus, average real or active power consumed by a pure inductor is actually the real part of the S. So P is equal to 0. This is what I have explained earlier here. All right, so we got 0 over here, and then this is 0 watts. And the reactive power consumed is actually the imaginary part of S again. So VRMS, VIRMS sine 90, which is 1. So we get finally the value of VRMS, IRMS, VAR. So note this result tells us that a pure inductor does not consume real. So does not consume real, P equal to 0. real or active. So we do have different terminology. We can actually refer to real or active power. The same thing. This is P, but consumes reactive power. Okay, so with positive value. So the compressed power S equal to JQ, in the same time P equal to 0. So there is no any real value, okay, because P equal to 0, but the imaginary value is there with JQ. All right, so S equal to JQ, the one in green. So this is JQ. All right, so the JQ, this is D. So this is the S. All right, this is the JQ. So positive value. So the third one is a complete power absorbed by a pure capacitor. So we have a capacitive element over here, linear capacitor. So let us again let the sinusoidal voltage of amplitude Vm and frequency omega equal to 2 pi f be applied to the capacitor where Vt sin omega t. So this is also again similar to Vt cos omega t minus 90 degree. So then the current flowing into capacitor is I C dV over dt. So we do have the value of the applied voltage. So just substitute into this equation, differential equation, and try to differentiate the value of Vt, Vm sin omega t, and we get omega c Vm cos omega t. So where I am here, all of this parameter can be simplified into Im. Okay, Im equal to omega c Cm. So capacitor in the time domain. So we have again the supply voltage, okay, with Vt or Vm amplitude. So we have the It over here, and this is how the phasor form looks like. So we have I over equal to I RMS 0 and V equal to V RMS minus 90 degree. So the phasor diagram for capacitor, 0 degree for I RMS and 90 degree, negative 90 degree for the V RMS. So that we can compare the behavior of the capacitor with that of the inductor. So now we're trying to compare between capacitor, the linear capacitor, as well as the linear inductor. So we will use V as the reference phasor and set its phase angle to 0. So we write V equal to V RMS 0. So here, okay, RMS, and I equal to I RMS 90 0. Okay, 90 0. So this is phasor diagram for capacitor. So how we got this one? So it's actually you try to shift, okay, you try to shift or try to make this V, all right, this V as a reference. So as a reference. So a reference means 0 degree. So now you try to make, again, you try to make this 90 degree become 0. So what you do is you just shift the V to here, okay. So once you shift V to here, so now become V over here, and automatically I will be shifted also by 90 degree. This is your new phasor of I. Right? Because once V is shifted by 90 degree up to here, okay, up to here, so I, which is initially located at 0, now become plus 90 degree. Okay, the same time being shifted also. Okay, so now this is how the phasor diagram for capacitor, the new phasor diagram for capacitor looks like. Okay, V become the reference and I now shifted by positive 90 degree. Okay, So complex power absorbed by a capacitor is again S equal to VI conjugate. I conjugate is the complex conjugate of current. So therefore I S V RMS 0 multiplied by I negative 90 degree. So we have over here initially is positive 90 degree, but once come to conjugate, right? So now it turns to negative 90 degree. Okay. So again, expand the equation. So we will get cos 90 degree and sine 90 degree for the imaginary part. Thus, the average real or active power consumed by a pure capacitor is P, the real part of S, VRMS, IRMS, cos minus 90 degree. This is equal to 0. Okay, because cos 90 degree is 0. Okay, and then the reactive power consumed is Q, imaginary part of S. This is the RMS, sine negative 90 degree. Again, this is minus 1. Okay, so sine minus 90 degree equal to minus 1 multiplied by VRMS and IRMS. So we will get negative VRMS IRMS. Okay. Then the power triangle for a pure capacitor. So this is the real part, this is imaginary part, X and Y. So since S equal to negative JQ, P equal to 0, so that means we only have the imaginary value, okay, located at the Y-axis with negative sign going downward. So it's going downward. Again, P is the red one is the P representing P and the green one representing Q. All right. So this result tells us that a pure capacitor doesn't consume real or active power but generates reactive power. Okay. So this is quite interesting. So whenever you find negative value of Q, okay, so this means that your load is, or your capacitor in this particular example, generating reactive power. So we have seen previous notes where during for the inductor, okay, this is for the pure inductor. So the Q is positive, okay. So Q is positive. Q in this particular example is positive. If we can go back to the inductor, so this is actually consuming reactive power. Okay, this is for inductor. And then again for the capacitor, so it is actually generating reactive power. Okay. So complex power absorbed by an inductive load. So consider a two-terminal inductive load over here. This is terminal of inductive load. So what is the meaning of inductive load? A load containing only inductance and resistance. So we have R plus J R, for example. All right. So having a driving point impedance given by the expression Z equal to Z theta degree ohms. So let a phasor voltage V equal to VRMS 0 degree be applied to the impedance. So the currents flowing through the impedance is obtained by using Ohm's law. This is as simple as Ohm's law equation where we have I equal to V over Z. So just substitute the value of VRMS as well as the impedance. All right. So VRMS over Z equal to minus theta degree. So let's say V of VRMS over Z is equal to IRMS, okay, where RMS is VRMS over Z. So we can simply say that this result tells us that current phasor I lags behind the voltage phasor V for an inductive load. Okay. So once we have solved this equation, so we simply get the negative value, and we can say that the I, all right, current is lagging behind the voltage phasor V for inductive load. Okay, so I is lagging behind. So thus, complex power consumed by the load is, again, S equal to VI conjugate. So Vrms 0, Irms theta. So Vrms, Irms theta. So average real or active power consumed by an inductive load is P equal to the real part of the S, Vrms cos theta. Expand the equation again. So the Q, reactive power consumed, is Q equal to imaginary part of S, again Vrms, Irms sin theta var. So this is how we can actually plot the power triangle for the inductive load. Okay, P over here, so this is Vrms, okay, Irms cos theta. Okay, this is a Q, green one, so this is the Q, green one, so Vrms, Irms sin theta, as well as the S. Okay, so the real power is consumed by the resistive component of the load, and the reactive power is consumed by its inductive component. Okay, so since we have two parts of complex power, namely P, so this is actually consumed by resistive component of the load, and this is consumed by inductive component of the load. Okay. So how about the capacitive load? So consider again a two-terminal capacitive load having a driving point impedance given by the expression Z equal to Z minus theta. So ohms, let the phasor voltage V equal to Vrms 0 be applied across to each two input terminal. So the current flowing through the impedance is obtained using, again, Ohm's law, I equal to V over Z, Vrms over Z minus theta. So we have now Vrms over Z theta. So just substitute the value of RMS, okay, into this equation. Okay, so we have IRMS with positive theta. So this is for capacitive load. So note that this result tells us that current capacitor I leads the voltage phasor the V, okay, voltage phasor V by some angle theta for capacitive load. Okay. Then complex power consumed by the load V S equal to VI conjugate. So now we have Vrms 0 and we have Irms with negative value. Alright, so we change the value instead of positive. Okay, now we have a negative due to the conjugate operation. Okay, now we have Vrms, Irms minus theta. So again, just follow the previous steps. So we have average real and active power consumed by capacitor load is P equal to real part, Q to the imaginary part. So again, P is cos and Q is sine. So now we have Vrms, Irms cos theta watts and minus Vrms, Irms sine theta. So for power triangle for capacitive load, so now we have the negative value of Q. Okay, this is somehow similar to what we have seen for the pure capacitor. Pure capacitor means only consists of capacitor, okay, or capacitive component. But this time around we do have both, again, the R, okay, component resistor, as well as the capacitor component, which is C. So combination between R and C, we do have R for the real part, okay, active or real power, as well as minus Q for the capacitor or capacitive element. Okay, so the real power is consumed by the resistive component. So this is what I said earlier just now, and the reactive power is generated by its capacitive component. Remember, so negative Q. So negative Q means reactive power is generated. Okay. So conservation of complex power in parallel circuit. So consider a parallel connected circuit shown below. So the complex power supply to the circuit is given by the expression S equal to VI conjugate. So where I star is the conjugate of the input current I for the current given. So the input current I is related to the branch currents I2 and I1 and I2 via the equation where I equal to I1 plus I2. This is simply from KCL, Kirchhoff currents law. So since we have two branches over here, I1 and I2, okay, so the total I, so this is actually I1 plus I2, okay, or you can simply write it over here. So hence I star conjugate plus equal to I1 conjugate plus I2 conjugate. So thus we can write S equal to VI. So VI, so I total. So break it down into I1 plus I2 all conjugate. So we do have VI1 conjugate plus VI2 conjugate. Or we can simply say that VI1 conjugate is actually S1 and VI2 conjugate is actually S2. All right. So this result shows for a parallel connected circuit. So we have branch number 1, branch number 2. This is a parallel connected circuit. The complex power supplied by a voltage, okay, source is equal to the sum of the complex power consumed by the load impedance. So we have S1 over here as well as S2 over here. So the total S, all right, the total complex power supplied over here S, this is actually S1 plus S plus S2. Right? And then conservation of complex power in series circuit. So consider series connected circuit shown below. So the complex power supplied to the circuit is given by the expression S, again equal to VI conjugate. I conjugate is the conjugate of the input current I for the circuit given. Voltage drop VI and V2 are related to the source voltage V via the expression. So we have over here I. Okay, we have Z1 load number 1 and load number 2, which is connected in series. So the voltage drop, okay, for Z1 is V1, and then voltage drop for V2 is for Z2 is V2. So we can simply sum up the value of voltage drop, okay, these two, which is equal to the sources V1. All right, so sorry, V over here. Okay, so V equal to V1 plus V2. Okay, so S equal to VI conjugate. So we total V is here. Okay, V1 plus V2. Okay, V1 plus V2. So expand this equation. So you still get V1I conjugate, V2I conjugate, whereas V1 I conjugate is actually S1 and V2I conjugate is S2. Okay, so this is to conclude that the previous two results can be generalized into a following expression. So S1 plus S2 plus S3 plus Sn. So whatever branches or whatever number of loads you have in your particular circuits, so the total is equal to 0. Okay. In words, this result tests out that the sum of complex power absorbed by all the elements of the circuit, for example, the voltage source or an independent is zero. So this statement is the complex power conservation law. So note that the statement complex power is conserved implies that both average power and reactive power are conserved. That is, so all elements, the sum of Pk power equal to 0, as well as the all element, the sum of Q, K is also 0. Okay. All right. So for the work example, so we will continue in the next video. Thank you very much for your kind attention, and hopefully you enjoy my video. Thank you very much.